Welcome, everyone. I'm excited to kick off today's presentation on machine learning. Today, we'll explore what machine learning is, its key concepts, and how it's shaping the world around us. The topic we'll be exploring is what is machine learning? As the title suggests, we'll dive into understanding this fascinating area of technology. Throughout the session, we'll look at what machine learning really is, how it works, and why it's so important in today's world. So let's get started and uncover the basics together. So why is machine learning such an important part of modern technology? Well, first, it enables automation of tasks that are either very difficult or even impossible to program manually. For example, image recognition, things like identifying objects in photos, would be incredibly challenging to code step by step, but machine learning makes it possible. Next, there's prediction. Machine learning can forecast future trends or outcomes based on historical data. Think about predicting stock prices or weather patterns. That's where these models really shine. Another key point is personalization. Machine learning helps tailor experiences to individual users. Ever noticed how your streaming service recommends movies you might like? That's a perfect example of how these systems create personalized content for each person. It also helps us uncover hidden patterns and insights from large datasets, things we might never notice just by looking at the data manually. This leads to smarter decision-making across many fields. And finally, machine learning is a powerful problem-solving tool. It's being used to tackle complex challenges in healthcare, finance, marketing, and beyond. Overall, these capabilities make machine learning a crucial driver of innovation and efficiency in today's tech-driven world. Now, let's take a closer look at how machine learning actually works behind the scenes. First, we start with data collection. This is about gathering all the relevant and sufficient data we need. The quality and quantity of this data are crucial because they directly impact how well our model will learn. Next comes data preparation. Here, we clean the data to remove errors or inconsistencies, transform it into formats that the algorithm can understand, and often format it in a way that makes pattern recognition easier. This step is vital because good data preparation sets the foundation for effective learning. Then we move to model training. We feed this prepared data into an ML algorithm, which then begins to learn from the patterns within the data. During this process, the algorithm adjusts its internal settings, these are called parameters, to minimize errors and improve its predictions. Once trained, we evaluate the model. This involves testing it on new, unseen data to see how well it performs and how accurate its predictions are. This step helps us understand whether the model is ready for real-world use or if it needs further refinement. After that, the trained model is deployed. This means integrating it into an application or system where it can start making real-time decisions or predictions. Finally, we don't just set it and forget it. We continuously monitor the model's performance over time, and when needed, we retrain it with new data. This ongoing process ensures that the model stays accurate and adapts to any changes or new patterns. All these steps are interconnected, and together they form the core workflow of how machine learning models learn, improve, and serve us in practical applications. Let's take a closer look at how a machine learning model actually works. First, we start with the training dataset. This is the data we use to teach the model, helping it learn patterns and relationships. Once the model is trained, we evaluate its performance using a testing dataset, which it hasn't seen before. This helps us see how well it can make predictions on new data. The core of this process is the ML model itself. It's the algorithm that learns from the data. After training and testing, we measure the accuracy, which tells us how often the model makes correct predictions. Now, depending on the accuracy, we can decide to deploy the model into real-world applications. High accuracy means the model performs well and is reliable, so we can confidently deploy it. But if the accuracy is low, then the model isn't ready yet, and we might need to gather more data or tune it further. Ultimately, this cycle of training, testing, and deploying is central to building effective machine learning solutions that can solve real problems. let's take a closer look at the main types of machine learning. First, we have supervised learning. This is where the algorithm learns from labeled data, meaning we have input-output pairs provided. The goal here is to predict an output based on a given input. For example, we might want to classify emails as spam or not spam, or diagnose whether a patient has a certain disease. In regression tasks, we're predicting continuous values, like estimating house prices or temperature. Moving on, the second type is unsupervised learning. This involves learning from unlabeled data, so we don't have predefined categories or outputs. Instead, the goal is to discover hidden patterns or structures within the data. For instance, clustering algorithms group similar data points together, which is useful for customer segmentation or market analysis. Another example is dimensionality reduction, where we simplify the data by reducing the number of features while still keeping the important information. Both types are fundamental to different applications of machine learning and help us solve a wide variety of real-world problems. Connecting this to our overall theme, understanding these core distinctions allows us to choose the right approach depending on the data and the problem we're tackling. Now, let's talk about reinforcement learning, which is a fascinating type of machine learning. In this approach, we have an agent that learns by interacting with its environment. Think of it like a kind of trial and error process where the agent takes actions and then receives feedback in the form of rewards or penalties. The goal here is for the agent to learn the best possible strategies or policies that will maximize its total rewards over time. To make it more relatable, imagine teaching a dog tricks. When the dog does something good, you give it a treat, and if it does something undesirable, it gets a correction or no reward at all. That's pretty much how reinforcement learning works in a nutshell. This method is used in a variety of exciting applications. For example, in game playing, like AlphaGo, where the system improves by playing countless games and learning from wins and losses. It's also employed in robotics, helping machines learn to perform tasks, and in autonomous driving, where cars learn to navigate safely and efficiently through complex environments. So, reinforcement learning is all about learning through interaction and feedback, aiming to find the most effective ways to achieve goals, whether it's a game, a robot, or a self-driving car. Now, let's explore some of the key applications of machine learning across various industries. In healthcare, for example, machine learning is transforming how we diagnose diseases, discover new drugs, and tailor treatments to individual patients through personalized medicine. It's truly revolutionizing patient care. Moving to finance, machine learning helps detect fraud more effectively, optimize algorithmic trading strategies, and improve credit scoring systems, making financial services safer and more efficient. In marketing, companies use machine learning for customer segmentation, creating more targeted recommendation engines, and delivering personalized advertising that really resonates with consumers. In retail, demand forecasting becomes more accurate, enabling better inventory management and reducing waste. Autonomous systems, such as self-driving cars, drones, and robots, rely heavily on machine learning to navigate and perform complex tasks safely. Natural language processing, or NLP, enables machines to understand and generate human language, powering sentiment analysis, machine translation, and chatbots that provide instant customer support. Lastly, computer vision allows machines to interpret visual information. Think facial recognition for security or object detection in manufacturing and autonomous vehicles. All of these applications highlight how machine learning is integrated into everyday life and industry, making processes smarter, faster, and more personalized, which ties back to our overall theme of how AI is reshaping the world around us. Now, let's take a look at some of the common machine learning algorithms that are fundamental to many applications, starting with supervised learning, which is where we train models on labeled data. One of the most well-known algorithms here is linear regression, which is used to predict continuous outcomes by finding the best fit line through the data. Then there's logistic regression, which, despite its name, is used for classification tasks like determining whether an email is spam or not. Moving on, decision trees and random forests are versatile algorithms that work well for both classification and regression. Decision trees split data based on feature values, creating a flowchart-like structure, while random forests combine many trees to improve accuracy and reduce overfitting. Support vector machines, or SVMs, are powerful classifiers that find the optimal boundary between classes, especially effective in high-dimensional spaces. K-nearest neighbors, or KNN, is a simple yet intuitive algorithm that classifies data points based on their closest neighbors. Neural networks, particularly deep learning models, are inspired by the human brain and excel at capturing complex patterns, making them ideal for tasks like image and speech recognition. Switching gears to unsupervised learning, where we work without labeled data to discover the inherent structure. K-means clustering partitions data into groups or clusters based on similarity, which is useful for customer segmentation or market analysis. Hierarchical clustering builds a tree-like structure of clusters, providing a different perspective on the data's organization. Lastly, principal component analysis, or PCA, reduces the dimensionality of data by identifying the most important features, helping us visualize and interpret high-dimensional datasets more effectively. These algorithms form the backbone of many machine learning solutions, and understanding them helps us choose the right approach for different problems. They connect to the overall theme of how we can leverage data to inform decisions and create intelligent systems. Thank you for watching. Like, share, subscribe to EC Learning 360 YouTube channel.